Every 4 computers now have primary control of critical vehicle functions.
All right, everyone, welcome to today's ASRG webinar. But before we get started, I'd like to tell you a little bit about ASRG and get some of the legal stuff out of the way. ASRG is a nonprofit organization founded to support the development of the automotive security industry. We have developed a platform and a community to share knowledge, communicate through networks, and to build value with collaboration. This is a community for you, built by you, with the goal to protect our friends and family when using automotive products. If you want to learn more about ASRG or get more involved, please visit our website at www.asrg.io or send us an email at hello@asrg.io. Before we jump into the presentation today, let's get some of the legal stuff taken care of. The views and opinions expressed in this webinar are the views of those that have made them. They do not represent views or opinions of ASRG and are to be considered as informational. The use of this information is to be used by the individual and/or organization at their own risk.
Hi, and welcome to the Spy Who Threat Modeled. I'm Heather Vermillion, and I have 16 years experience in a variety of industries, including Department of Defense, e-commerce, big tech, and insurance. I've said it before, and I'll probably say it again, automotive and transportation, critical infrastructure, this is my favorite industry to be in by far. There are lots of exciting opportunities and exciting problems to solve. I really like to focus on the foundations of a good security program, so really getting the basics right. And I think we've got a lot of opportunity where we can really do some good work here. So I want to jump right in. Vehicles, we know, are big, complicated machines, and the design process reflects that. The output of this process is as varied as anything, from motorcycles to passenger cars. We have the long-haul trucks to the off-road specialized heavy-duty mining equipment and other heavy-duty machines. This V model here has been super effective in that vehicle design for a long time and producing vehicles that are both functional and, with some notable Pinto-sized exceptions, safe. Now, of course, us security engineers are being asked to make these things secure as well. We already have a functional safety process, and it sort of follows that security is a related discipline and should go about the same, right? Right, except for all the ways that it's different. Functional safety, by definition, takes a look at that physical aspect to make sure that road users are as safe as houses or as safe as we can make them rolling down the road. Security focuses a little bit more on that digital space and this whole software-defined vehicle concept. And ideally, of course, security would be part of the conversation from the very beginning, right at that concept phase. Unfortunately, reality has ensued, and we got dropped halfway through this process for our next model years, give or take a few years, depending on what your OEM is doing. Of course, for the next cycle, we can start right at the concept phase, but that's probably a few years off if you're already in the motion of getting the next model year out, right? And that also doesn't do much for the millions of vehicles that are already on the road, including the ones that are rolling off the line right now. So here we are. We have to do the best that we can. And if we have to bolt security on, which is not what security likes to do, then we at least need to start in this process where we are and define what our requirements are, which is to say we need to figure out what is the most critical aspect of vehicle security and go about protecting that. We have to ask what can go wrong. We have to threat model. So, like us, poor Q didn't get to start with the concept design of the DB5 for Aston Martin. All he had was Bond winning it at a poker game and said, here, and he had to figure out what could 007 possibly get into, where could he reasonably be found, and how can I best protect him given the technologies and the options that we have. So that's exactly what we have to do in threat modeling. First, though, I want to take a quick detour into a brief history, because how did we end up where we are today? First, we invented the car in the late 1800s in Germany. Whole 25 years later, we got the Model T in any color we liked, as long as it was black. 60 years after that, we started sticking computer chips in these vehicles and in these engines to better control valves and fuel injection, the ignitions. And this is when the engines really started to get smart in the late 70s. And then various other regulations came into being around things like emissions, basic safety, maybe we should wear seat belts, operator licenses, maybe we should, make sure people know how to drive these things. So a lot of regulation back in the 80s and the 90s were around those topics because they were very front of mind. Fast forward 30 more years, and we figured out that if the computers started to be in charge of things like functional safety, maybe we should look and make sure that they're as safe as the mechanical aspects of them as well. So we got ISO 26262, which is the functional safety of road vehicles, and that came out in 2011. And we don't want computers to cause harm to any humans. So 26262 established the concept of identifying the hazards and assigning risk levels in that vehicle design process. And then only 4 short years after that, Charlie Miller and Chris Valasek remotely hacked a Jeep on the highway, and it all went sideways from there, because clearly the clause of the second law of robotics, which is obey humans unless it conflicts with causing harm to humans, needed implementing on top of that functional safety, and fast. So only 5 years after the Jeep hack, we got the ISO 21434, which is the cybersecurity engineering of the road vehicles, giving us a baseline for us in the industry to figure out how to actually do that. How do we make these vehicles secure? And only a year after that, governments started getting in and say, hey, maybe we should put some regulations around this as well. So we have EU came out with UNECE 155 and 156, the cybersecurity and cybersecurity management systems. And it kind of turned that ISO, hey, we really think you should do this, into we're going to do it, and we're going to check up on you and audit you and do all of those other processes to make sure that you, the OEM, are doing the right thing. So now we're kind of here. And this is clearly a fast evolving field, and security has got to keep up, because self-driving cars are already kind of here, and the ways that they can go wrong have absolutely littered pop culture for generations, right from the Jetsons to the Fast and the Furious movies and numerous other references I could make. So clearly, us humans have some thoughts and feelings with autonomous cars and autonomous cars going wrong. So we have to address the concept. And I'm talking about this right up front because I think it's important to remember the context in which us security folks are trying to adapt. We are evolving this field sort of in real time, and we're figuring it out as we go. Ain't it grand? So what I like to do is strip back the complexity, because vehicles are big, complicated messes. So the first step in doing our threat assessment is to look at what can possibly go wrong. So what does a vehicle even do? We expect to have some basic functions. We expect it to go. We expect it to stop. We expect it to steer. And if we want to get fancy, we can throw in things like shifting gears, any of that engine power transfer for those additional components, any onboard diagnostics, basic functionality. So we've got that we can look at. We also have the area of functional safety we can look at, because we do expect a modicum of safety in our vehicles. We expect things like seatbelts and airbags to work perfectly, exactly as designed, every single time. So we expect things not to crash, and we expect to be able to fail safe, not necessarily secure, but safe. So that is something that could possibly go wrong. We expect not to be able to shift from like sixth gear at highway speeds right into reverse. We expect not to be able to do that because that would be a huge problem. And if we want to get fancy, we can look at the different areas like the driver assisted features, the lane keep assist, the forward collisions, all of those other things that we're packing on in sort of that level 2 autonomous zone. So those are all possible things that we can look at to see, hey, what can we possibly do here? We can also look and see the threat intelligence, like what are the attackers actually doing? So that's one way we can focus all of this big complicated mess into, all right, what's actually going on? Let's address that before we move on. So largely, vehicles are still seeing a lot of theft. No real surprise there. There's that whole Kia Boys TikTok challenge nonsense. There was another automotive security researcher who had his Toyota stolen with an injection attack. So he got a whole talk out of that. You should go watch it. It's fabulous. Remote takeover is a concern. It's rarer than theft, but it's still a major cause for concern. And driver privacy is very quickly becoming an issue. It's getting some attention in the US Congress, and it's getting attention in some of the states as well. So if we look towards the future for threat intelligence, we can see, hey, the autonomous driving, that's only going to get more and more frequent. I'm sure most OEMs have an autonomous driving program in place. So look at that. Look at all those components. What can possibly go wrong that's going to impact all of our vehicles? So what is not on this list is all of the edge cases. So who I like to call the three stooges of car hacking, otherwise known as Jeremy Clarkson, Richard Hammond, and James May, who will take a perfectly fine car, in this case a Reliant Robin, and strap space rockets to it. The gearheads that want to tune their engine so they can get a little bit more performance out of it, and other driver shenanigans that they're going to do what they're going to do with the aftermarket bits and bobs that they put on the engine. I say bits and bobs because I'm not a gearhead. But that's not on the list. Those aren't really things that we want to spend our time worrying about, because unless they're off making a TV show, these aren't going to happen. People aren't going to be taking cars and strapping them to rockets. I hope not anytime soon. So in enterprise, we have a whole host of indicators of compromise and tools that can look out for threats. We've got a well-established vulnerability database to say, hey, we know when this bad thing is, we know what it looks like, and we can put alerts in to watch out for it. So us security people are used to thinking about those very specific threat scenarios, the vulnerabilities in the software, and we know what to do with those. We plug the indicator of compromise into the detection system, and we watch for it to happen again. Unfortunately, that sort of body of knowledge, that working knowledge, we're still kind of building that when it comes to vehicles. So we have to go back to the foundations to look at the actual functionality of what the vehicle is supposed to be doing. And I'm talking about the basic functionality. We can add in all the other crazy scenarios later. So here is our map for an easy 8-step process. We're going to play the role of Q, and we need to figure out what we can add to our Aston Martin that just suddenly showed up at the door to keep Bond safe and allow him to complete the missions. And so this is going to be our guide through our journey today. And I put this map in place because each one of these steps feels a little bit like step 1 is draw a couple of circles, and step 2 is draw the rest of the owl. So we're going to walk through and use our Q and Bond as an example to figure out what's actually going on in this process. So the very first thing we need to do is look at the scope of what we're doing. We need this item definition. And this is starting from a vehicle level, and I'm keeping it simple on this slide. Because if I put a big architecture diagram up, if you're a vehicle security person at an OEM, or even at a supplier working with an OEM, you've probably seen that big architecture diagram for an engine model that is an absolute like eye chart mess. Great design, but it's got a lot of components to it, right? And so if you haven't seen something like that, you're going to need it. Ask any design and architecture folks. They're probably good sources. They'll know where to find it. Another great source to get started on your item definition is functional safety, because ISO 26262 also requires that these item definitions, so any component that's been through functional safety should have an item definition. And fun fact, ISO 21434 was written by some of the same folks who wrote 26262. So there's a lot of similar processes here. So the functional safety people can really be a great resource. So here, Q doesn't have the benefit of having that confidential architecture diagram. So he either has to reverse engineer it or just, I guess, as MI6, ring up Aston Martin and say, can I have it? So here, again, we're going to keep it simple just for the sake of our example. It is a good idea to spend some time to study that big picture and figure out what's going to what and what's interconnecting with what, because there are huge component systems that if we drill down into them, they're going to have other components within them, and they're all going to be tied together in kind of some crazy ways depending on what needs to happen in the design. There's probably going to be more than one CAN bus in the engine, and some components won't be able to reach others. Here, I kind of arbitrarily picked a couple components that would reasonably talk to each other, because I imagine the engine's going to be able to talk to the engine controller, will talk to the brake controller and figure out how to not have the engine going when you're hitting the brake, because that would be counterintuitive. And that may not go through a gateway, right? That might just go directly to between those components because it needs to. So really spend some time to figure out what connects to what and what components can impact the others. However, like I said, that high-level diagram's probably a big spaghetti mess of connections. You've got wires going everywhere. So if we're trying to focus on just one component or another, it's helpful just to look at that. So here I've kind of drilled into this engine powertrain system. So if we look at the engine management system, it's got various components in and of itself to keep the engine running smoothly and control the engine. So it's going to talk to the ignition. We're going to talk to the gear shifts. It's going to have some kind of timing thing to make sure all the valves in there actuate properly. And if we can keep drilling down into any one of these components until it's a manageable amount that we can reasonably threat model in a single session or in, a short amount of time. So there are a lot of systems on a vehicle, and it really is impossible to threat model everything all at once. So the key here is to remember that systems are connected, because you can see I've got that connection going back up to the main vehicle level from the engine, because it's going to flow back up to some kind of gateway and then into another system. So as you complete threat models for any one of these components, you may have to go back and update other threat models that you've done before, and that's fine because things are going to change as you go. So, quick map check. We've sailed right through the first step, and now we're on step 2. And here's where we can really start diving into our example, because what kind of trouble can 007 possibly encounter? So our first step is to identify, our second step after the item definition is to identify these damage scenarios and figure out what can possibly go wrong, and identifying the assets and any cybersecurity properties that confidentiality, integrity, and availability assigned to these different damage scenarios. Most of what I have here on the slide are confidentiality or availability related, because if we get our MI6 information stolen, that's going to be bad for confidentiality. If we get the vehicle blown up, then we don't have the vehicle anymore, so that's availability. So we're really looking at that whole full asset of the car, that vehicle level, as well as our dear 007. So we have some damage scenarios. We've brainstormed those. Now what? Now we get into the threat scenarios, which is step 3. Now it's really time for some imagination, because any one of those damage scenarios could have any number of threat scenarios that lead to that damage scenario. So if the worst possible thing that can happen is 007 getting captured, how could he possibly get captured? You can just brainstorm ideas. You can use some tried and true stride model to generate ideas. Don't necessarily overthink it too much, because we don't want to try and come up with an exhaustive list of threat scenarios. We're going to get diminishing returns after a certain point. So here I've come up with 4 different ways that Bond could get captured. So one of the villain's henchmen could catch up to us and, throw a pair of handcuffs on Bond, throw him in the trunk and take him out to the villain. Maybe it's towards the end of the movie and the main villain, Goldfinger, has spotted us and could capture him directly without having to use any of his henchmen. Maybe Bond just runs out of ammo and he's backed into a corner, and he can't get out without shooting his way out, and gets captured there. And maybe he really needs some kind of quick exit, again, getting back into a corner, not necessarily with his weapon this time, but again, if you're backed in and you can't find that quick exit, then you're gonna get captured. Right, I hope you're with me so far. We have made it almost halfway down already, the impact ratings, and here's where it'll start getting a little bit complicated. So ISO 21434 gives us these 4 different areas of impact that we can think about when doing our impacts ratings. And the Appendix F of that document goes into detail about how to define each one and define each of the levels. The options are negligible, moderate, major, and severe, which is a really fun way of saying low, medium, high, and critical. Now, if we go back and look at 26262, in their clause 6, we can look at a couple of other factors as well, because we can look at safety exposure, and that's got 5 levels ranging from that's going to be a really weird fluke to it's definitely going to happen. So we'll look at more at the exposure when we do the attack path analysis. 26262 also defines controllability and has 4 different levels, again, low to high, to look at the probability that the driver, Bond, will be able to avoid any one of these impacts if they can gain sufficient control over the situation. So, and here again, we can see a little bit of the thinking where 21434 kind of came out of 26262 because safety is one of our impact ratings. I did rate that severe because if Bond gets captured, then he could face serious or even fatal injuries, and that's pretty severe. We also look at operational impact. In this case, I'm looking more at the car, and I'm thinking, well, engines don't really like to continue to go forward if they're full of bullet holes, so that's also going to be severe. And we can also look at privacy and financial, and these are rated a little bit lower for our example, because there's not a whole lot of PII that we're dealing with, just location, maybe VIN number, license plate, and for financial impact, I mean, he can just go win another one at poker, right? Or bill it to MI6. So even though it is that custom made with all of Q's modifications, it's certainly not going to be easy to replace, but he's not an average Joe on the street either. And if we're looking at exposure factors, that's going to be pretty high, because when does Bond not get into a car chase with some of the henchmen? So that's probably going to happen. And controllability, probably going to be about normal, because Bond's going to try his best to get control of the situation and reasonably extract himself. So another way to look at this is, who is actually going to impact it? Is it going to be the road user, or is it going to be the, maybe we're looking at a reputation hit for the OEM. Maybe this is going to be a hit to Aston Martin because they don't want to see their cars explode in the news, because I'm guessing no OEM wants to see that, right? So you can look at these impacts all kinds of different ways, and from what I understand, it was intentionally left a little bit vague so that you could adjust it to your needs and adjust and see where your impacts are going to be maybe a little bit higher. Because as we go forward in this process, you'll be able to see that it's not going to be a straight like 1-for-1 when we look at our feasibility and our likelihood. So this is our impact rating, and so in this case, it's going to be severe and moderate. Another quick map check. We're going to keep doing this all the way through the process. And now we get to look at attack paths. So how can these threat scenarios come into being? We've identified what they are. We can identify all the ways that it can impact us should it come to pass. And now we can dive more into how likely is it going to happen. So here I brought this diagram back because we can see our damage scenario at one side is getting captured, and we can see our other threat scenarios here. But each one of these threat scenarios, there can be multiple attack paths, multiple ways to accomplish this threat scenario depending on what's happening. So if the henchmen are going to catch up to Bond, there's generally going to be two ways that's going to happen. Either the henchmen are going to go faster, or Bond's going to get slowed down. So the henchmen can either drive faster or take some kind of shortcut, or they can slow Bond down by setting a trap, running him off the road, and maybe some other ideas. Again, don't overthink it necessarily, but just try and come up with different ways that the threat scenario can be accomplished. Hope everyone's still with me so far. We're all the way down at the bottom with attack path feasibility ratings. So here it starts getting a little bit complicated. So I really looked at the Appendix G in 21434 for the guidelines for this feasibility analysis, and that's where all of these ratings and numbers have come from, and I'll get into that in a minute. So we're going to follow the guidelines for the attack potential-based approach. So if the attack path involves some kind of vulnerability with a CVSS score, you can use that instead. Attack vector is another way you can look at it, and that just looks at the scale of physical access required. So if it required physical access, there's guidelines for scoring that, or if it was something that could be accomplished fully remotely, there's guidelines for scoring that. But for the sake of this example, I chose the complicated one to kind of talk through. There are 5 different areas to consider, 4 of which I put on the slide. The last is equipment, which has values that range from standard equipment to multiple custom pieces of equipment. So for the most part, this is going to be straightforward enough. Most vehicle equipment is more specialized than standard IT security kind of gear, but once we're in this space, that gear is very standard, right? That specialized gear is readily available. And for the purposes of our example here, that gear is going to be extremely standard because all the henchmen need are another car and some weapons of their very own. So that really didn't add much to the score, so I left it off. So the first pair I kind of want to talk about is time and window of opportunity. Those are subtly different because time is the time the attacker spends from discovering the vulnerability to and developing the exploit and then setting it all up. Whereas the window of opportunity is more focused on actually performing the attack. So you've spent maybe 6 months finding and developing this really cool exploit, and then you get up and to actually execute it, and you have 2 minutes to get in and get it done. So that 2 minutes is going to be your window of opportunity versus your 6 months of research that goes into that 2 minutes. So in our case, how straightforward is it going to be to lure Bond into a trap versus how much time is it going to take to scout the maps, find a great place to set up a dastardly trap, and get all those components in place, because that could take a lot longer to do. So when we're looking at taking a shortcut, that's probably going to happen on the fly, right? So it's not going to take any time to develop. So under 1 day, and that gets a score of 0. Versus setting a trap, again, that may take a little bit longer, but probably not over 6 months. Probably they're not going to spend that much time setting up their dastardly plans, but probably more than a week, under a month, give or take. So I said under a month, and so that gets a score of 4. And again, all of these numbers are coming straight out of that appendix. Versus the window of opportunity, that may be a little bit difficult to time and take the shortcut right then and there in the middle of the moment, in the heat of the moment where, the henchmen are being fired on and they're firing back and they're driving really fast and they have to corner real sharp. So that's a little bit harder to do. So I selected moderate. Versus running Bond off the road, that takes a lot of driving skill, a lot of window of opportunity to get right up and slam the cars against each other and actually get them off the road properly instead of onto another road to continue the chase. So that's going to be a lot more hard to pull off. So I rated that difficult at a 10. So because a lot of that window of opportunity is going to be timing just right to make sure that you can pull it off without getting caught. So expertise and knowledge are also subtly different, because expertise is the overall capabilities of the attacker. We would expect the henchman to have the same kind of expertise as the main villain. They may have more or less in certain areas. They may have a greater expertise in doing that offensive driving, and maybe a little less in critical thinking. We don't hire henchmen for their critical thinking skills. Versus knowledge is how much information is known and how hard is it to come by that info. So if again, your architecture diagram, that's probably confidential information that you're not going to post out to the internet. So that's going to be a little harder for that attacker to come by. So here I'm saying maybe that knowledge area is maybe we're setting up a trap on some private property. The maps aren't readily available, or last time the maps were updated was 3 decades ago when some old European town and all the roads are wrong and the rivers are wrong. So maybe that's just not updated, not available. So I rated those a little bit higher. So then once we've gone through each one of our attack paths, so taking a shortcut, driving faster, setting up a trap, and running Bond off the road, we go through all of those areas, and then you just add. So if we look at take a shortcut, we've got under a day, that adds nothing to 0. Expertise got a 3, knowledge got a 3, window of opportunity got a 4, so we get 10. And again, there's a table in that appendix, and that gives the breakdown between high, critical, moderate, and low. All right, we are approaching the bottom of this easy bake-off process. Step number 7, risk analysis. So now we have to decide which risks are we going to address, because we only have so much time and resources. So we have to pick and choose which ones we're actually going to do a risk treatment for versus the ones that we can very comfortably say risk accepted. So remember here that risk is impact by probability. So now we combine our impacts from step 4 with the probabilities we just got in step 6. So here I rated critical and critical. Driving faster, that's very likely to happen. It's very easy to just put your foot down and go a little bit faster, maybe less so if your foot's all the way on the floor, but still pretty critical. Probably going to want to address that one. Versus setting a trap and taking our shortcuts, there's still definitely overall high risks looking at the impacts and the probability, but they're like different kinds of highs, right? Because one, take a shortcut that's got a pretty high impact, pretty high likelihood of happening versus the actual impact, maybe not so much. Versus the trap, we have a more higher impact of actually getting Bond to stop so we can capture him. So that is a little bit higher, but they're both still overall high. And remember with the impacts, there's a little flexibility there to say, all right, which impact am I going to choose? Because there were 4 different components there. That's safety, the privacy, the financial, and the operational. So you can pick a high watermark. There was a couple severes, a couple moderates in there. You can pick one that's most important to the threat model, or you can take an average. So again, there's a lot of flexibility for exactly how you want to come up with that overall impact versus the probability, so you can come up with which risks that you want to address. So I rated the run off the road, more of that low. The overall risk is lower because I needed to put something in the lower category. And finally, we are at the end of our process. We are in step 8, risk treatment. Now, for a little bit of the fun part, we get to decide how we're going to address these different risks. Notice that some of those risk treatments overlap. So if you look at set a trap and take a shortcut, best thing we can do as Q is put some radar in there. Like, let's put some radar that can ping off and see where the different things are. Maybe it's not radar, maybe it's LiDAR, whatever technology we have, and we've stuck our radar scanner behind the mirror, and we've stuck the screen in the dash so Bond can see everything as he's driving, so he knows where to avoid. So that takes those risks from a high level, maybe down to more of a moderate, or depending on what that radar can see, maybe even a low, which is fantastic. Versus the critical, the henchmen are going to drive faster and catch up to Bond and catch him. We've got a little more options here. We can do cool things like spit out a smoke screen, we can spit out an oil jet, some caltrops, anything to slow the henchmen down so that as they're trying to drive faster, we're slowing them down in return to address that. So again, we're taking that critical all the way down to, I don't know, moderate. Moderate sounds good. Again, this is where it gets a little fuzzy, but that's okay. But it definitely takes that risk down to a level that we're way more comfortable with than that, oh my god, critical. So, and the same with that medium. Maybe the henchmen are trying to run Bond off the road, and you've seen those car chase scenes. They get up right next to each other and they try and bump the car off. So Bond's Aston Martin's got some tire slashers in there so that when they try it, he can pop their tires instead. So again, it takes the risk down from that medium, maybe to a low. So we're protecting ourselves even more. So that was a lot of process, right? So what do we need to do this process for? This threat assessment and risk analysis, TARA. You need to do it for everything, unfortunately, is the bad news, because any component that can impact that security risk is going to need going to need that Tara. And again, as I showed, maybe some of them overlap in some manner. So the components are going to interact with each other. Cars aren't designed in a vacuum. They don't operate in a vacuum. They're all about connecting those different systems together. So we have to think of that big picture while we're going through and doing this. I started with a top-down approach, starting from that vehicle level, and then we kind of drilled into some of the things that could possibly happen. Starting from the bottom up, also a completely valid method. It doesn't really matter which one you do, as long as you pick one and stick with it and be methodical about it. Because it's possible that the threat scenarios and the damage scenarios, they're going to roll down. So as you drill down into the different ECUs, they may contribute to a damage scenario or a threat scenario that maybe you'd already identified on another component. So if you start from bottom up, you're going to find things that are slowly rolling up into that top vehicle level and that are going to affect that basic functionality of going forward, stopping when we want it to stop, and turning when we want it to turn. So it's all going to interact together. So just remember that when you're doing the TARs for the different components. And yeah, that means running a Tara on all of the components in the architecture. And yes, I said up top that it was a bit of a spaghetti mess of all the different wires going everywhere because vehicles are big, complex machines. And it can be a little bit daunting to go through the process, and especially when you look at the process and it's just an easy 8 steps, right? Unfortunately, it's the only way to get a complete picture of all the risks that are affecting a particular vehicle. And that means not just the ones that are under a current redesign or a design refresh, that means all of them. And this is why the tooling and the automation are important. Talk about that in a second. You really want to focus in on the places where these components connect and interconnect, because it's going to be those integration points that could lead to the biggest damage scenarios. So we already know we're in the deep end here. We've got a lot of information on, like I said at the top, that architecture diagram for the whole engine. It's a big mess. We need some gadgets and some tools and some automation ourselves so we can keep all of that information straight. Because like I just said, the models can overlap between the different components that we're working with. I know a lot of folks are using spreadsheets and flowcharts. There's nothing Excel can't do. But Excel is a very great Swiss Army knife of security tools. There's nothing it can't do, but that doesn't mean that it does them well. So ideally, we'd like a tool that's a little bit more designed for this process that we just went through. Because as we're working through the different models, we're finding things that overlap and maybe roll up to each other, roll down to other components. That's all great. It can save ourselves work as we get deeper into threat modeling all the different components, but we have to remember where we put our homework, because if we lose our homework, then we just have to do it again, and that doesn't save any time. There are tools out there specifically designed for threat modeling. Microsoft has a great one. It's free, which is great, and it's also super flexible, which is also great because that means that we can adapt it for the vehicle space. It is more focused into that IT enterprise kind of space. So when you get in there, it's going to have a lot of like cloud-based things. It's going to have a lot of Azure-based things, and there's not really a whole lot of Azure clouds sitting inside of an engine. So you absolutely can add those other components in there and make it work for you. It is also very Stride based because Stride came out of Microsoft, which is fantastic. That part's already programmed in, but if that's not the model you want to use, you have to spend that time to set up the model that you want to use. So I have found that that one requires a lot of care and feeding to work. It does a lot of customization. It can work very, very well once you've got it to the point where it can do what you want it to do and have all of that automation for you. We do have tools designed for threat modeling vehicles itself, which is awesome. But what I have found from working with them, and this isn't disparaging any of those tool makers, but you still need a lot of that pre-knowledge from this process, from the ISO 21434, even with your own vehicle architecture design. You still require a lot of that background in order to make full use of those tools. So they still have got a steep learning curve to them. Now, of course, your actual architecture diagram and your actual components, that is all completely proprietary. You have to go to your OEM or your tier 1 to look at those. But we can absolutely learn and study this process, which is hopefully what I have tried to demystify today. I also want to have a quick sidebar for IT and OT, because everything that connects to the vehicle also has to get type compliance for that regulation UNECE 155 and 156. So we still have to do that threat modeling, even though it's an IT component, but it connects into our product, it connects into our operational space. And like I just made the distinction between having that Microsoft tool versus our vehicle-specific threat modeling tools, the threat modeling does look a little bit different depending on which space that we're in. And so, yeah, this was a lengthy process that we went through, but it's fundamentally not that different from regular IT threat modeling. We're still finding impacts, we're still finding impact probabilities, we're still determining risk, all of that kind of basic foundation, that's still the same. So in the IT space, if you're looking at, say, annual loss expectancy, single loss expectancy, you have a quantitative method, you have a qualitative method, and all these different ways to come up with your impact and your probability. That's all different ways of doing what we just talked about. So the foundation of that process is going to be the same, even if some of the exact details of how you come up with those impacts and probabilities are a little bit different. So, that's great, because that means that as an organization, you don't have to write and maintain 8 different policies and procedures and standards just to do threat modeling. You can write your policy and your procedure for it once, and you can apply it to the different areas as you need it. And of course, I did want to talk about some easy wins here, because what can we do that we already know that maybe we don't have to go through this whole process in order to get to the risk treatment at the end? Disable things that we don't need. And that goes from all of our software, from our API connections, all the way down to that hardware level. So again, maybe it's the folks in the factories, your folks at the suppliers, to disable those JTAG ports. If you don't need them, don't put it into the production model. I say that like it's common sense, but as I'm sure many researchers will attest, they go and they get those used components off of eBay. There's a solid chance that it's still going to be enabled. So that is an easy win to put in a policy and maybe an audit process to check, are we disabling all of the interfaces that we don't use? And that's something that we can sort of add on as we're going into this V model. We didn't start off at the concept phase. We can also say that, hey, maybe separate the devices if they don't really do the same things. I know a lot of attacks come in over the infotainment devices because those are right on the dash. They're easy to get to. Maybe don't have the infotainment connect directly to the engine control units, the engine management systems. So separate those. Again, in IT, we're very used to thinking, oh, okay, let's separate the things onto the different networks to keep them separated so we keep them both safe. Same concept applies here. And use cryptography properly. Hopefully I don't have to belabor this point. Let's not roll our own crypto to put into our cars. There are libraries out there. Let's just use those. as well as lock down any supporting systems. So, like I said, none of these products, none of these vehicles operate in a vacuum. They operate in a whole world of connected things. So it's going to have, maybe you have over-the-air updates. That means you've got an update server back there. You probably have some kind of diagnostic tool that when you have to take your car into the shop, the mechanics are going to hook up to see what's wrong with the car. So all of those supporting systems deserve just as much of attention as anything on the car engine itself. And lastly, I say this is an easy win. It's probably not that easy. Just using the diagnostics and the monitoring wisely, because if we look at some of the trajectory in the IT space, one of the big things that we've had to worry about there is that living off the land. Bring your own vulnerable driver. So making sure that when, and I'm not saying to get rid of diagnostics, because we absolutely need to have those in there, but making sure that as we put in those different fault codes, those different CAN messages, that we're making sure that we use it wisely and we're not accidentally giving attackers additional tools in order to give ourselves better ways to diagnose problems. So it's kind of like not telling folks which of their username or password was invalid, just saying credentials invalid. That way you're not giving any hints away when when attackers are going in and trying to do that reconnaissance and trying to gather that information. So that brings us right to the end. Key takeaways here is don't try and dive right into that big diagram and threat model everything at once. Break it down into some kind of manageable chunk where you can wrap your mind around it so that you can keep it all straight. Don't overthink it. Don't make it more complicated than it has to be. It's really not any different than what security folks have been doing already. It's just in a different space. So it looks weird, it feels weird, it seems different and hard, but I promise you it's not. And when in doubt, ask for help. Like I mentioned a couple of times, your functional safety folks have been going through this already. They probably have a lot of really mature processes in place. So lean on them, lean on their lessons learned, figure out what worked, figure out what didn't, figure out what work you can borrow, because if they've already done a bunch of item definitions, go ahead and take those so you don't have to recreate them. And also remember that this is a continuous process. These threat models aren't something that is one and done and it's going to sit on the shelf and gather dust, because we're going to keep having more information come in. There's the Automotive vulnerability database that the ASRG maintains. The Auto ISAC has the Automotive Threat Matrix. So those products keep getting updated. So we're going to have to keep using our threat modeling and keeping those up to date as well. Like I said, as you threat model other components, you may have to go back and add in some threat scenarios or add in some attack paths that you maybe didn't think of the first time. So this is going to be an iterative process, and that's okay. And finally, perfect is the enemy of good enough. We don't have to come up with everything all at once. We don't have to worry about people putting perfectly good cars onto space rockets. Need to just focus on the basics here. We can get to all of that fancy stuff later. And again, it's going to be an iterative process, so don't worry so much about getting it perfect right off the bat. It's going to be okay. And that's all I have. Thank you for coming to my talk. Any questions?